Modern gasoline direct injection engines deliver incredible horsepower and fuel economy until severe carbon buildup chokes your intake valves, triggering violent misfires and a $4,000 repair bill. Traditional port fuel injection never had this fatal flaw. Here is the hidden engineering trade-off behind direct injection, why your valves are baking in sticky carbon, and how to stop it. To understand why modern engines are literally choking on their own operational byproducts, we have to examine how fuel delivery evolved over the last 3 decades. For generations, the automotive industry relied on port fuel injection, often abbreviated as PFI. In a traditional port-injected engine, the fuel injector is mounted inside the intake manifold, positioned just upstream of the intake valve. Every time the engine calls for fuel, the injector sprays a fine mist of gasoline directly onto the back of the hot intake valve. As the valve opens, the moving piston sucks that pre-mixed cloud of air and fuel past the valve and down into the combustion chamber, where the spark plug ignites it. This system is simple, reliable, and mechanically forgiving. But as strict government emissions regulations and aggressive fuel economy demands pushed automakers to squeeze every drop of efficiency out of smaller engines, port fuel injection hit a physical wall. Enter gasoline direct injection, or GDI. In a direct injection engine, engineers bypass the intake manifold entirely. The fuel injector is moved out of the runner and threaded directly into the cylinder head itself, pointing straight into the high-pressure combustion chamber right alongside the spark plug. By spraying gasoline directly into the cylinder at extreme pressures, often exceeding 2,000 to 3,000 pounds per square inch, the fuel evaporates instantly. This rapid evaporation creates an intense local cooling effect inside the cylinder. Lower cylinder temperatures suppress engine knock, allowing engineers to raise compression ratios, advance ignition timing, and bolt on high-boost turbochargers without causing destructive pre-ignition. On paper, direct injection is an engineering masterpiece. It yields a 10 to 15% increase in engine torque, significantly boosts gas mileage, and reduces cold start emissions. But this efficiency boost created an unintended, catastrophic side effect inside the cylinder head: the carbon buildup disaster. To pinpoint why direct injection engines suffer from aggressive carbon buildup while port injection engines remain spotless, we need to look at 2 intersecting physical factors: the detergent washing effect and PCV oil vapors. In a traditional port fuel injection system, gasoline acts as a continuous cleaning solvent. Commercial gasoline sold at gas pumps is blended with chemical detergent additives designed specifically to dissolve carbon, varnish, and sticky combustion residues. Every single time a port injector pulses, it bathes the back of the intake valve in fresh, high-pressure detergent fuel. The valves are continuously washed clean hundreds of times per minute while the engine runs. In a direct injection engine, that chemical detergent washing effect is completely gone. Because the GDI injector sprays directly into the cylinder, fuel never touches the intake manifold, the valve stems, or the back of the intake valves. The intake valves are exposed purely to dry, incoming atmospheric air. If incoming air were completely clean, this wouldn't be a problem. But modern engines are legally mandated to recycle their own toxic internal vapors through the positive crankcase ventilation system, the PCV valve, and the exhaust gas recirculation system. As your engine operates, high-pressure combustion gases slip past the piston rings into the oil pan below. To prevent the crankcase from exploding, the PCV system pulls these volatile gases out of the oil pan and routes them back into the intake manifold to be burned off. These PCV vapors are saturated with microscopic droplets of suspended motor oil, raw hydrocarbons, and unburned fuel vapor. As these oily PCV vapors pass through the intake manifold of a direct injection engine, they coat the hot, dry intake valves. Intake valves regularly operate at temperatures between 300 and 600 degrees Fahrenheit. Without any gasoline detergents to wash that oil away, the intense heat bakes the oil droplets directly onto the metal stem and tulip of the valve. Layer after layer, drive cycle after drive cycle, that baked oil transforms into a hard, sticky, porous crust of solid carbon. Within 30 to 50,000 miles, clean metal intake valves become completely encrusted in thick black carbon sludge. The accumulation of carbon on intake valves isn't just an ugly visual issue when a mechanic snips a borescope camera down your intake ports. It triggers a cascade of severe mechanical performance problems. First, carbon buildup fundamentally alters the fluid dynamics of incoming air. Engine designers spend millions of hours engineering smooth, polished intake ports that create precise air turbulence inside the cylinder for complete combustion. As carbon crust builds up, it acts like rough, coarse sandpaper, creating heavy drag and restriction. Air flow drops significantly, starving the engine of oxygen, choking top-end horsepower, and creating sluggish throttle response. Second, solid carbon is highly porous. It acts like a hard industrial sponge. As fresh air enters the engine, these carbon deposits absorb moisture and atmospheric pressure, disrupting the precise air-fuel ratio. Third, and most dangerously, heavy carbon crust prevents the intake valves from seating flush against the cylinder head. Intake valves must form a gas-tight hydraulic seal against the hardened valve seat to contain the intense pressure of combustion. When hard chunks of carbon wedge between the valve face and the seat, the valve cannot close completely. High-pressure combustion flames leak past the unsealed valve, burning the edges of the metal valve face, a condition known as a burned valve. Once a valve burns or warps from localized heat buildup, the cylinder loses all compression. The engine begins to misfire violently, idle rough, illuminate a flashing check engine light, and lose power under load. Furthermore, as chunks of hard, petrified carbon inevitably flake off the intake valves due to vibration and heat cycles, they fall directly into the combustion cylinder. These hardened carbon rocks can lodge between the piston ring lands, scoring the delicate cylinder walls and causing premature oil consumption. If they pass through the exhaust valve, these solid carbon fragments strike the high-speed turbine wheel of your turbocharger, or slam directly into the delicate ceramic lattice of your catalytic converter, causing secondary component failure. This brings us to one of the biggest misconceptions spread across automotive forums and online parts stores: pouring fuel additive bottles into your gas tank. Drivers notice their direct injection engine running rough, head to an auto parts store, buy a high-concentrate fuel system cleaner, pour it into their gas tank, and expect it to clean their crusty intake valves. Mechanically, this is completely useless. Remember, in a direct injection engine, the fuel goes straight from the fuel rail into the combustion chamber. Fuel poured into your gas tank never touches the back of your intake valves. You can pour 50 bottles of high-end fuel injector cleaner into your gas tank, and not a single drop of that cleaning detergent will ever make physical contact with the carbon crust caked on your intake valves. While fuel additives will clean the high-pressure GDI injector tips inside the cylinder, they are physically incapable of cleaning GDI intake valves. So, how do mechanics actually solve this issue once carbon takes over? The industry gold standard for restoring a carbon-choked GDI engine is a manual procedure known as walnut shell blasting. To perform this service, a technician removes the entire intake manifold to expose the individual intake ports. They turn the engine's crankshaft by hand until the intake valves for a specific cylinder are completely closed, sealing off the engine cylinder below. Using a specialized pneumatic pressure wand, the technician blasts crushed, fine-grained walnut shells at high speed into the intake port while pulling a continuous vacuum. The walnut shells are hard enough to shatter and strip away the baked-on carbon crust from the steel valves, but soft enough that they will not score, scratch, or damage the underlying aluminum cylinder head. After several hours of blasting and vacuuming, the valves are restored to bare metal shine. However, a professional walnut blasting service routinely costs between $600 and $1,200, a recurring maintenance tax unique to direct injection owners. Recognizing that customers were growing frustrated with recurring walnut blasting costs and valve failures, automotive engineers began developing both factory-designed solutions and preventative maintenance strategies. The most effective factory solution available on modern cars today is dual-fuel injection, often called PFI-GDI hybrid systems, such as Toyota's D4S system or Ford's dual-fuel EcoBoost designs. Instead of picking one system, dual-injection engines install two injectors per cylinder, one direct injector inside the cylinder and one traditional port injector up in the intake runner. Under heavy acceleration or high-load conditions, the engine computer utilizes the direct injector to maximize horsepower, boost, and knock resistance. But under light cruise or idle conditions, the computer fires the port injector. This secondary port injector sprays detergent-rich gasoline over the back of the intake valves, permanently washing away PCV oil vapors and completely eliminating carbon buildup, while retaining all the power benefits of direct injection. If you drive a standard direct injection vehicle without dual injection, you must adopt an aggressive preventative strategy to protect your engine. 1. Use premium full synthetic motor oil with low NOACK volatility. NOACK measures how easily motor oil vaporizes under extreme heat. High-quality synthetic oils evaporate far less, drastically reducing the volume of oil vapors passing through your PCV valve. Look for oils meeting API-SB or ILSAC GF6 standards designed specifically to combat GDI deposits. 2. Install a high-efficiency oil catch can. An aftermarket oil catch can tease into the PCV line, routing oily vapors through a series of internal baffles and wire mesh filters. The oil droplets condense inside the can rather than coating your intake valves. 3. Shorten your oil change intervals. Never wait 10,000 miles to change your oil on a GDI engine. As oil ages, it breaks down, thins out, and vaporizes far more easily, accelerating carbon formation. 4. Perform intake valve foam cleaners early. Chemical foam cleaners sprayed directly into the intake throttle body can help dissolve light, soft carbon if performed every 15,000 miles, before the carbon bakes into petrified rock. Direct injection is a triumph of modern internal combustion engineering, unlocking levels of power and efficiency that were thought impossible decades ago. But that high-tech performance comes with a strict mechanical price. Without the continuous detergent bath of traditional port injection, your engine relies entirely on clean oil and preventative care to keep its air passages breathing freely. By understanding the physics of PCV vapors, avoiding useless gas tank additive myths, and maintaining your oil system, you can enjoy the power of direct injection without falling victim to the carbon buildup disaster. If you found this technical breakdown valuable, hit the like button, share it with a driver, and keep your intake valves breathing clean for miles to come.